Professor Pete is a professor of physics at the University of Toronto. Their research interests include string theory and the quantum theory of gravity. Specifically, Professor Pete works to apply string theory to black holes. They are also an affiliate of the Premier Institute for Theoretical Physics. They are the 2017 recipient of the Terry Buckland Award for Diversity and Equity in Education and the Radcliffe Institute for Advanced Study Fellowship, among other awards. Professor Pete received their PhD at Stanford in 1994. And Professor Pete would prefer if you take questions at the end. So if you have a question, just note down the slide number, and at the end, you'll be able to ask away. Take it away.
Okay, well, I'm really honored to be here. Thank you so much for the invitation. I hope what I can give is a bit of a flavor of what it's like to do research, thinking about the deep interior life of black holes from the perspective of somebody who's interested in the overlap region between quantum physics and gravitational physics. And so if you want to not take notes during the talk, all you need to do is write down this slide URL here where all the slides are available now, for example. And hopefully it'll be useful for people who maybe their attention wanders to come back to the slide. They can look at what I'm discussing. Maybe I can start by just saying a couple of things about what kind of scientist am I. Well, a scientist is always a function of background and training and also their own interests. I grew up in Aotearoa, which is an archipelago or a chain of islands in the South Pacific Ocean, more recently known as New Zealand. I trained at the University of Canterbury in New Zealand and then went to America for basically the 90s, where I did my PhD at Stanford, as mentioned, and then I did postdocs at the Princeton University Physics Department and at the Institute for Theoretical Physics at the University of California, Santa Barbara, before I joined the faculty of U of T about 20.5 years ago, where I'm now a full professor of physics. Identity-wise, I'm like 52 years old, of Welsh, Scots, Irish, and English ancestry. I'm trans and bi, autistic and disabled. So when I was coming up in undergraduate, people said you basically had to pick a side. You had to say, well, you know, I'm either interested in theoretical physics or more interested in experimental physics. But now in 2021, since computational power has come so far since then, there's really more three zones to where people often focus their interest when they say they're a physicist. And so there's computational, experimental, and theoretical, and the last one is my jam. So I'm most fascinated by aspects of theoretical physics, how the various forces and particles and so forth in the Standard Model and also gravity, how they work. And so I classify myself as a theoretical subatomic physicist, or alternately a theoretical high energy physicist. And I'll let you decide as to whether you think the high energy refers to the particles that we study or the people who do that studying. And as mentioned in my research, I recruit mathematical techniques to address questions about the deep interior life of black holes. And my motivations really come from just pure blue sky, imaginative theoretical physics curiosity. I don't have any particular expectations that my work will end up leading to breakthroughs in quantum computing or anything else. The blue sky curiosity is sort of good enough of a motivation for me. One of the questions that we always think about when trying to address the questions that we're interested in is what toolkits do we pick to be doing our analysis? Now, I'd just like to dispense with one myth right at the beginning of my talk and say, no, I'm not one of those subatomic physicists who claims the mantle of doing the most fundamental science or even the most fundamental discipline. I think that kind of attitude is pretty arrogant. The more honest truth about what we do is that different toolkits are appropriate for studying different phenomena. Like, for instance, we wouldn't be using the same kind of techniques to study Higgs bosons, mitochondria, and human societies. So as a tenured professor in STEM, I want to be clear that I also value academic contributions in other fields, including social sciences, humanities, and the arts, and also knowledges held by other long-standing communities outside of academia, for example, Indigenous nations that have lived in these lands for thousands of years. My main research interest, I want to understand the subatomic structure of space-time. Another word for that is quantum gravity. So there are quite a few ponies in the race to describe what quantum gravity is. And the pony that I bet on is called string theory. And I'm interested in using that toolkit because it's versatile, and the field has also fruitfully overlapped with so many other parts of theoretical physics, during the 3 decades or so that I've been in the field. But I must say I'm not married to string theory. If it turned out that another theory of quantum gravity came along tomorrow that was actually better for all the purposes that we're interested in, then, well, maybe I'd actually switch ponies. So string theories had overlap with particle theory, which it actually grew out of. Strings were initially invented around the same time that I was, although that's just a coincidence, to try to describe the forces that keep quarks bound inside atomic nuclei. With the strong force, there's overlaps with mathematics, especially all sorts of areas of geometry, with gravity theory, with early universe cosmology theory, and even more recently in my lifetime academically and in condensed matter theory, and most recently of specific interest to people in my field has been overlaps with quantum information theory. So if we're interested in studying black holes and the quantum physics thereof, black holes involve gravity, and the theory that we have nowadays to describe that is known as general relativity. That's one of the pillars of 20th century physics, if you like, and another of those pillars is quantum mechanics. So general relativity describes the physics of very heavy things. It was invented a bit over 100 years ago and has successfully described a great many experiments, including bending of light by the sun, which Newton's theory gets wrong, for example. General relativity, the theory of it, conceptualizes gravity not as some scalar potential thing that teaches us about potential energies, but instead in terms of the smooth geometry of the fabric of space-time itself. So space-time is no longer just a static stage on which the other things, which we call matter, that's just to distinguish them from gravity. So the stage of space-time is not just an unbending static thing. In fact, it's dynamical. And the equations of GR teach us that space-time tells matter how to move, while matter tells space-time how to curve. Interestingly, general relativity is a nonlinear theory of gravity, which means that more exciting things can happen than are possible in Newton's theory of gravity, which only covers weak gravity situations and slow speed situations. And one of the things that GR has is black holes. So great, they've got the animals that we're interested in. That's part and parcel of Einstein's theory of GR. Now, quantum mechanics is arguably about a rather different realm. It describes the physics of very small things, and it was invented a bit under 100 years ago and has also successfully described and explained a great many experiments. Quantum mechanics teaches us that at small scales, life is granular and full of quantum jumps. For example, if you look at the energy levels of atomic electrons, they can only take specific values. So if you excite an atom, like maybe neon in a sign outside a shop, and then it relaxes back to an unexcited state, it emits the energy difference as light with a very specific frequency that's specific to that atom called a spectral line. Quantum mechanics also has a fundamental randomness baked into it. The classical notion of clockwork determinism, as imagined by Newton's theory of gravity and of motion, that becomes superseded. And what it's replaced with is quantum determinism, which permits us to precisely calculate pertinent probabilities for what we might find when we do a measurement, but they don't describe with certainty what's going to happen. There's an aspect of probability to the physics of very small things like electrons and silicon chips inside your smartphone. So let me now look into some of the aspects of black holes and what makes them interesting from this perspective of a subatomic theorist like me and colleagues. So 2 important things about black holes are really important to know. I'll just mention, you may have noticed that last year, half of the 2020 Nobel Prize in Physics went to Sir Roger Penrose for co-discovering that Einstein's theory of general relativity robustly predicts that black holes will be formed. And in my slides, I'll just call them BHs for short, just that I don't have to spend so much space talking about black holes. So black holes occur out there in the universe when big stars run out of gas to burn and they collapse under their own weight. Inside a region called the event horizon, if you're inside that region, you can't escape the gravity of the black hole, not even if you're moving at the speed of light. So light gets trapped inside the event horizon of the black hole, and everything slower than light also gets trapped. Now, a bit further out from the event horizon of the black hole, light tends to pile up, and that's basically what the Event Horizon Telescope collaboration imaged for this big black hole in another galaxy. Now, that actually isn't a picture from the Event Horizon Telescope. It's a screenshot of a graphic from the movie Interstellar, if you want to actually see some very beautiful plots of what the motions of light and the buildup of light at these places for a rotating black hole, then they actually spent millions of dollars of supercomputer time producing these gorgeous graphics. So at the time the film came out, I actually took my grad students to see it in the big theater so that we could see the big graphics rather than having to watch it on a smaller screen at home. So there's the event horizon, which is basically the surface of doom. If you fall in, you're never coming out. And at the heart of a black hole is another signature characteristic of that space-time, which is called the singularity. And that's a curvature singularity where the very fabric of space-time gets, infinitely curved. And there's extremely strong shredding forces, otherwise known as tidal forces. They're the same forces that actually produce the tides on Earth, just much, much stronger. And even the nuclear forces are not strong enough to resist the enormous shredding forces associated with black holes, especially near the singularity. Now, even if you had a black hole and you were an astronaut falling in from the outside, if you've got a black hole that has about the same mass as our sun, those shredding forces are already strong enough to kill you even before you fall across the event horizon. What happens is that you get stretched out along the direction of motion towards the center of black hole, and you get squished in the other direction, so you basically turn into a bunch of spaghetti of little subatomic constituents. Now, at a theory, that's already kind of disturbing, so just make sure that you don't go near any black holes, and there aren't any black holes very nearby, so we're not in danger of falling into any. I had to remember once when I gave a talk to school kids not to frighten them about the prospect of a black hole coming and scaring them in their dreams. Sometimes black holes scare theoretical physicists, So the violence of the curvature singularity, the place where the fabric of space-time is literally infinitely curved, that signals a bit of a problem with the theory of general relativity. Because at and around the singularity, a curvature singularity, the equations of general relativity don't actually predict what happens. And they actually kind of fall flat on their face and can't sensibly answer good physics questions. So one of the questions is, does that violence associated with the singularity always remain hidden behind the event horizon of the black hole? It's a really good question. And one question that imaginative theorists like me ask is even, does space-time even stay four-dimensional near the singularity of a black hole? Now, unlike in Chris Nolan's movie, I don't think that the fifth dimension is describing love. Sorry, that was a spoiler. I guess by now you probably had a chance to see the film if you wanted to anyway. It's got an imaginative rendition of what it might feel like to go through a black hole. So one of the big puzzles that people like me have worried about is a puzzle raised by Stephen Hawking, which he came across about 1974 or 75. And why do we think about black holes? In order to try to get our thinking, to refine our thinking about the subatomic structure of space-time, in other words, with quantum gravity. Currently, we don't have any direct experimental access to that realm. We've only got, at best, indirect access to experimental access to questions about quantum gravity. So we need to exercise our imaginations in a thought experiment lab to really be able to get our ideas in order before we even ask the experimentalists to go look for signatures. So if you solve some equations of general relativity in 4 dimensions, which is, after all, the dimensions we live in, 3 dimensions of space and 1 dimension of time, it turns out there's only 3 types of properties that you can actually see about a black hole from very far away. One is the mass, another one is the angular momentum, and if there happen to be any charges that the black hole can carry, this wouldn't be electric charge, but there can be others, then those also would be visible from very far away from the black hole. But that's actually all we can know about the black hole by looking at it from the outside. And Stephen Hawking decided to say, well, suppose I have this classical black hole solution of Einstein's equations, and then I just imagine that, what if it interacted with quantum things like, I don't know, photons, the particles that make up light, visible light, and other parts of the electromagnetic spectrum. And let's say, well, the black holes and the photons could talk to each other. And what he discovered by doing quantum physics with matter along with the classical black hole space-time is that black holes emit thermal radiation. This was a pretty big surprise. It's a quantum effect, and it happens even if there's nothing else in the universe, like no accretion disk or not even any other, stars or galaxies or anything around. Even the black hole, just by itself, would emit stuff. And the interesting part about Hawking's radiation, well, one of the interesting aspects, is that again, it only knows about those three things: the mass, the angular momentum, and if any, the charge on the black hole. So here's the puzzle that arises when he thought about it all those years ago. He said, well, suppose I've got a black hole with a given mass. Make it simple, just don't have any the other stuff turned on for that black hole, just a massive black hole. And let's suppose that I throw a textbook on black hole dynamics into the black hole that weighs 1 kilogram. Then the mass of the black hole would increase by 1 kilogram. And then if we ask what kind of Hawking radiation comes out of the black hole, that's supposed to be the right part of the picture. I'm kind of a bit elementary about my ability to draw graphics, so hopefully that gets the idea across. What you get out is bland Hawking radiation, and it only knows about the mass that you added. So Hawking said, well, what say I did a different experiment, a thought experiment, and instead of a 1 kilogram book, I chucked in a 1 kilogram orange roughy fish from the waters off New Zealand. Well, then you'd get exactly the same Hawking radiation coming out. And he said, well, what this implies is something pretty profound, is that the difference between books and fishes, after all, is, important. That kind of information, and actually a whole bunch of other types of information that I might throw into the black hole to make it or add to it, is that it seems like these classical black holes that I'm talking about, they do emit this bland kind of thermal radiation, but it doesn't tell you much about what's inside the black hole. So he said, I propose that classical black holes eat quantum information. Now, particle physicists found this pretty depressing because we, have bias reasons to expect that this sort of thing shouldn't happen. After all, if you're trying to do the microscopic theory of the universe, you shouldn't kind of lose track of probability or degrees of freedom or things like that. So we found it quite upsetting and have been spending decades trying to amend that issue and see how, with a better understanding of quantum gravity, we could see that, in fact, maybe information isn't lost. It just comes out in a very scrambled way compared to when you sent it in. So there's a lot to say about that, but I want to get on to moving towards the next my story. And so I'll mention something else that people discovered also in the 70s about black holes. And the idea came up that they said, well, if Hawking has showed us that a black hole is a temperature, then maybe we can think about it as some big macroscopic thermodynamic system. People in physics had admitted this idea, the ideas of thermodynamics, in the later half of the 1800s to help them to design and build more efficient heat engines, like, make a steam engine more efficient. And one of the concepts that was useful for them in trying to codify how much energy input heat that you might waste before you can make some work, like moving a train along some rails, was an idea called the thermodynamic entropy, which has the symbol S. And this entropy encodes basically the degree of disorder of a system. For example, ice, which assembles itself, at least ordinary ice, at our atmospheric temperatures and pressures, it has a quite ordered crystal structure, whereas liquid water, all the molecules can mess around and be in very different configurations. So we say that the water has a higher entropy than the ice. Also, if you had a teenager with a tidy bedroom, that would be an example of a low entropy situation, where if it was all messy and everything was flung all around, that would correspond to a high entropy bedroom. Now, Ludwig Boltzmann discovered a general formula in the 1870s, which by now is quite a long time ago, like 150 years ago, for understanding the entropy of some macroscopic system in terms of a number of the microscopic ways that you could make that system from its little tiny microscopic ingredients. And he said, well, if there's W ways of making that state of the system microscopically, and I take the natural log of it and multiply by a constant that became known as Boltzmann constant, then he said, that's the entropy. And it turned out to describe some systems that physicists were very interested in understanding, like gases inside a piston. And he was so proud of this formula that he had it engraved on his tombstone. Now, a century later, building on a series of really important works by Jacob Bekenstein, a precise formula for the thermodynamic entropy of a black hole was found. And it turned out to be some physical constants, blah, 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 times a quarter, times the area of the event horizon of the black hole. So the bigger the area of the event horizon is, the more entropy it holds. And this entropy here is quantifying our ignorance about what lies behind the event horizon of the black hole. I don't think that the formula is especially interesting, except to point out, I mean, yes, it's proportional to the area, and that's an interesting thing that I'll remark on later, but it also involves the Boltzmann constant, which is a thermal physics thing. It involves the speed of light, which is a relativistic thing. It involves h bar, which is a constant of quantum mechanical phenomena. And it involves the strength of the Newton constant, teaching us about how strong gravity is between, say, a couple of protons. And Hawking's formula, finding the temperature of the black hole, finding it precisely, was really crucial to getting the precise coefficient in that formula. And so the big question that people came up with, back then, and that took a long time for a good amount of progress to be made on this, was to say, well, if that's the macroscopic description of the entropy, and there's really good reasons developed over years to imagine that that is the true thermodynamic entropy of a black hole, how do we explain it from first principles? If we could build it from some microscopic ingredients from a theory of quantum gravity, then if we're really smart, maybe, and if we're very good and get what we want for Christmas, we might be able to count the number of microscopic ways to make that black hole out of its the macroscopic black hole out of all those little microscopic ingredients. And then if we take the log, hopefully we'll end up getting the correct entropy. And that's a thing that was discovered for some classes of black holes in a bit over 20 years ago. So to dig into a little bit the question of the quantum gravity, I have to mention a small number of things about quantum physics, because that's actually very pertinent to all the things that we want to know. So let's consider just one electron all by itself, or say a quark or any other subatomic particle. So how do we tell it apart from other subatomic particles? How do we know that it's an electron, for example, and not an up quark? Well, we know by the mass, and that technically, for those of you who are on the ball, is the rest mass. There's also the spin and any charges that it might have, for example, electric charge or red, green, and blue charge under the strong nuclear force, or a weak charge, isospin and hypercharge, for example. And the key thing about those three properties of subatomic particles is that they're the same in all frames of reference, regardless of your relative motion between your frame and somebody else's frame. So they're good labels for a particle because we're all going to agree on them. Spin is a tiny amount of intrinsic angular momentum that's quantized, and you can't dig it out of the subatomic particle. It's not like an angular momentum of a top, which you can slow down if it has friction with the table. That intrinsic spin is something that's intrinsic to the character of the particle, and it can't be removed. Now, subatomic particles with odd or even integer times this quantum of spin are called fermions and bosons. The odd ones are called fermions, and the even ones are called bosons. And fermions make up matter. That includes electrons, protons, neutrons, quarks, and neutrinos. And bosons play the role of force messengers. And so if you take a system of bosons or fermions and cool them down to extremely low temperatures, they behave very differently. For example, fermions turn out to need some personal space from one another. They obey a thing called the Pauli exclusion principle, which means you can't put them in the same place at the same time in the same quantum state. Bosons, on the other hand, they can even go into a group hug if you cool them down cool enough, and that's called a Bose-Einstein condensate. So those are some properties of fermions and bosons that are important to our story. So let's also imagine that we were able to measure the spin of an electron along some axis, like is it pointing upwards or is it pointing downwards? Classically, the spin would be measured as up or down. And when people actually started studying, it got smart enough experimentally to be able to study individual electrons, they found that actually in quantum physics, the real physics of the subatomic realm, is that in fact, the electron is in a coherent superposition of both spin up and spin down. And this is an example of a qubit, and the coefficients in that sum of the coherent sum of upspin and downspin teach you the probability of seeing spin up or spin down when you measure it. And just very briefly, quantum computing aims to harness this kind of quantum coherence to be able to compute things faster using qubits rather than classical binary bits, which could either be 1 or 0. Now, microscopic objects like electrons or atoms or sometimes even molecules can have quantum entanglements with one another. These are sort of spooky influences. that aren't there in our normal experience of macroscopic things like dogs and baseballs and cars. Quantum entanglements can persist over large separations. For example, in a famous thought experiment called the EPR experiment, you produce two photons going off in opposite directions that are entangled with one another. And if you happen to measure the quantum state of one of them, you would instantly know the quantum state of the other one. But in fact, this entanglement can't be used to transmit messages of information faster than the speed of light. And that's basically because there's a probabilistic thing that if you measure the spin up of an electron, well, you didn't know whether it was going to be spin up or spin down. And that's one of the reasons why you can't use that spooky quantum entanglement to violate fundamental speed limits of causality. Now, quantum mechanics, you've also probably heard of a thing called Schrödinger's cat. Have any of you sort of heard of that? I think probably you might have, at least in the popular sphere. I have to say that it's a little bit misunderstood as it's often referred to in the popular sphere, but isn't that always the case with technical things in science? But to begin with, I would like to say that I do have to question the research ethics of a thought experiment where a life-death decision about an animal relative of ours is treated quite so casually. I think it's important that whenever we think about thought experiments, we don't imagine violent things that we do to other living creatures, at least have some ethics about that. For example, if I'm thinking about sending an experimenter into the black hole, it probably should be a professor who makes the sacrifice rather than a graduate student. Anyway, the key point of the imagined contraption called the Schrödinger's cat setup is basically to link up this mysterious microscopic probabilistic quantum behavior, the radioactive decay of an unstable atom in the original thought experiment. And what they were trying to do was with this contraption to link that up to classical behavior in the macroscopic realm, the life or death of a cat. After all, if we have a cat in front of us, if we're a vet, we can measure whether it's passed away or whether it hasn't. And we don't ordinarily go about seeing cats in a macroscopic superposition between alive and dead. That's just not what we see macroscopically. So somehow what's going on here is a bit of a mind-bending experience, and it hurts our brains because this whole setup unrealistically assumes that nothing else exists in the universe around these objects that could spoil that quantum coherence. And that's basically what happens as you get a system bigger and bigger and bigger, that those spooky quantum entanglements end up having to die off, because we do know that at macroscopic length scales, you don't see the professor in a state of both alive and dead at the same time, or on the Zoom call and not on the Zoom call at the same time. I'm actually here at the moment. I'm not here and I'm not dead. Okay, so the fascinating general question that Schrödinger's cat really gets at is, where is that transition region? Where does the physics of the system stop being quantum mechanical and start behaving classically? So where does the microscopic change over into the macroscopic? And a question that's interesting to theorists like me to think about, but it's also even interesting to people who are trying to build quantum computers. Can we engineer systems experimentally, or if not, at least theoretically, where this crossover happens more slowly, perhaps? We don't lose quantum coherence so fast, allowing us enough time to do some important quantum computations, or maybe at a larger spatial scale than we might originally have guessed. And that's the kind of question that people like me are actually really interested in. Where is the classical to quantum transition for gravitational physics? And does it depend on the precise gravitational system you study? In a word, the answer is yes. So in physical systems with a really large number of microscopic constituents, you might find surprises. You might find qualitatively new behaviors might emerge in a technical sense of emergence when you have a large number of constituents. And this is part of the story that we play with when we're thinking about quantum gravity. So what is quantum gravity? It's a really good question to think about. One of the first guesses that you might have is, well, what if I take Einstein's perfectly great theory of general relativity, which, while we didn't need it to land men on the moon, Newton's theory was good enough for that purpose. But if we want to describe a much broader range of physical phenomena than just moving from a planet to a moon, we want to describe even solar system tests like the precession of the perihelion of the planets, Newton's theory is not good enough for that, and we do need Einstein's theory. So what if we just try to use Einstein's theory as a quantum theory? Well, if you study it, you'll discover that in fact, quantum physics and general relativity are basically fundamentally incompatible. At a qualitative level, that's because general relativity is all about the smooth fabric of the geometry of space-time, whereas quantum mechanics has that randomness and that quantum jumpiness built into it. Is really baked in, just like the smooth fabric of space-time geometry is baked into Einstein's theory of GR. So if you try to just put these two ingredients together, you'll discover that if you're interested in very short distance physics or equivalently very high energy physics, then you'll find that interactions involving gravity grow out of control. And what you'll obtain from the quantum theory is some nonsensical pieces of physics, answers to physical questions, where, for example, the probability for something happening would be greater than 100% or negative. And I don't know about you, but if I've computed a probability that it's going to snow tomorrow and the answer I get is 120% or minus 40%, then I probably made a mistake in doing my calculation. So this isn't just a minor niggle, it's actually a deep theoretical emergency, like having roads governed by incompatible traffic rules. So you might say, well, can't we just sweep this disagreement under the rug? How about we let general relativity stick to governing very heavy things only, and we'll let quantum mechanics stick to governing very small things only, and just optimistically pretend that there isn't any overlap between those two things? Well, there are actually two situations in the universe where we've got something that we're interested in that is both heavy and very small. And that is black holes, number one, and the Big Bang itself, which was what happened when our cosmos was originally created. And string theory is one way of resolving this theoretical emergency that GR and quantum mechanics don't go well together. And that what it does is it says, well, I'll stick with quantum mechanics as the guiding principle. I think that shouldn't be old. And I'm going to modify the theory of gravity at short distances so that it's different from general relativity. But at all the long distances where we've already done measurements of gravitational physics described really well by Einstein's theory, then we get that back at long distances, but the only modification to the physics is at short distances. So this is where string theory enters the picture, is again one of the toolkits that we can use to describe quantum gravity. So to motivate it, I'll just ask you one question that might seem kind of impertinent, and that is, you've probably been told when we're thinking about subatomic particles that those are the most elementary constituents imaginable of what we see in front of us in terms of the structure of matter. And we're told that electrons and other elementary particles are point-like, in other words, they have zero dimensions to them. Now, how do we actually know that these things are truly zero-dimensional? Well, the short answer is we don't. The only way to know that for certain is to be able to do physics at all length scales, including infinitely short distances. But even the Large Hadron Collider, which is our most powerful machine in existence for studying subatomic physics, that can only probe down to about 10 to the minus 20 meters, which is a billionth of a meter, and then about 1% of that. So that's a very, very small distance, but we don't actually know, beg your pardon, if something like an electron is truly point-like at distances below that scale. So string theory impertinently says, well, let's suppose that the Legos of the universe are not zero-dimensional point particles, but instead they're very tiny one-dimensional vibrating strands of energy, and these are known as fundamental strings. Now, why do we use the word fundamental? Just to distinguish it from the cat string, which is macroscopic string that your cat plays with. These little strings are to be thought of as very, very tiny, smaller than 10 to the minus 20 meters, for example. And if we took our glasses off and looked at this tiny little string that was vibrating, then to the resolution that we could see, it looks just like a point particle. But if we were able to look with our high resolution glasses at this string, then what we would see the one-dimensionalness of it, rather than just seeing it look like a zero-dimensional thing. And why is this idea? Here is that you only really need string, one kind of string, to be able to represent all the known subatomic particles, and even more than that. So strings can have either no ends to them, where they're shaped like a rubber band, going around the universe doing their little vibration, or the strings might have ends to them. You have to imagine that these are the two ends of the string, and there could be endpoints of the string which could be dancing around. And the ones with ends are called open strings, and the ones without ends are called closed strings. How imaginative. Yes, string theorists didn't think of whimsical names for those, at least. And if you look at the lowest mode of vibration of a quantum open string, you'll discover that it can describe the photons that transmit the electromagnetic force, the gluons that transmit the strong nuclear force binding nuclei together, and also the W and Z bosons that transmit the weak nuclear force in nuclear fusion, and even the Higgs. The ground state of a closed string, by comparison, and this is where the money shot comes in. If you just look at the quantum physics of the very lowest state of oscillation of a closed string, you'll discover that it describes gravitons, which are the messenger particles for the gravity force. And so if you start from string theory as your Legos and you work through the physics of making a consistent quantum theory of strings, which wasn't understood, by the way, until 1984, you'll discover that you predict gravity. Now, of course, we're not impressed, because humans discovered gravity experimentally and theoretically long before we thought of the idea of string theory. So nope, sorry, string theorists aren't getting a Nobel Prize for predicting that gravity exists. That's sort of a bit of a, a passe thing that we've known for a long time. String theory also predicts extra dimensions of space that are tightly curled up and hidden from view, at least in our current universe. Now, strings can wrap around these curled up dimensions, and that can have quite profound consequences for what quantum space-time looks like. Sorry, there seems to be something in the Q&A which maybe I should look at. I'll try and answer that later. I'll just stick to what I'm looking at now. So one thing to mention, by the way, about string theory is actually more than just strings in string theory. This wasn't discovered until about 1995, and that ushered in what was called the second superstring revolution, where we learned how to do new things using string theory. And there are things in the theory called branes, which is just short for membranes, higher dimensional objects than strings. And in particular, one of the branes that's available in string theory is called D-branes. And the name where it comes from is a little boring, so just bear with me and use the terminology for now. They turn out to be places where open strings can end. And these things have a tension to them. So if you try to poke the D-brane and deform it away from its equilibrium position, it will want to come back to equilibrium, and they can vibrate and have oscillations and interesting behaviors. And you can work out what happens for D-branes just by knowing that open strings end on them. You don't have to add any new physics principles to understand the physics of D-branes. Now, D-branes can gravitate. And in particular, if you can pile a whole bunch of D-branes on top of one another, I've separated them a little bit in my attempt at drawing a picture just so that you can see that there's a bunch of them there. But let's imagine that they're all on top of one another like this, like pieces of paper. And you can ask, how much do those branes warp the fabric of space-time? After all, they have a tension to them, and because they have a tension, which is a mass per unit volume, then that can gravitate. And so the amount of gravity that the stack of D-branes makes depends on how close you get. If you're very, very far away, the gravity is weak, but if you're very close up, the gravity is strong. And the amount of gravitation of warping of the fabric of space-time that the branes live in happens is proportional to how many branes you've got. So even if a parameter called the interaction strength of strings is very weak, then as long as you've got a very large number of branes, you can make big, fat classical spacetimes from D-branes. And it turns out that building macroscopic black holes using strings and D-branes was one of the things that I was involved with in the late 90s, and a lot was learned about it that led to some pretty important discoveries. So I mentioned a bit ago that there was this thermodynamic entropy of a black hole, this Bekenstein-Hawking formula that had this macroscopic understanding, but there was really no microscopic understanding of how to count the number of ways you could make that thing. In 1996, Andy Strominger and Kumran Vafa, both based at Harvard, used quantum statistical properties of strings and D-branes to derive the entropy for the associated macroscopic black hole from first principles. This was the first honest-to-God computation from first principles anything from quantum gravity for explaining the Bekenstein-Hawking entropy of a black hole. They originally did it for specific types of theoretical five-dimensional black holes with charges. And that breakthrough was later broadened significantly by other people, including for four-dimensional theoretical black holes. And a few months later, some people, Sumit Das and Samir Mathur, found out that the standard equations of string mechanics allowed you to study outgoing radiation. For example, if you had some open strings, whose ends are on the D-branes that happened to join up and find each other, then under certain conditions, they could escape from the stack of strings and D-branes, and they ended up playing the role of Hawking radiation, and you obtained the Hawking temperature from this string and D-brane model of black holes. So the amount of progress that was made in those several years led Stephen Hawking to concede a very famous bet that he had made with John Preskill, who is a quantum information theorist and somebody who studied quantum gravity in black holes based at Caltech. And in 2004, Hawking said, okay, I give up. You guys are right. Black hole information, because of these string and D-brane models, probably isn't lost. It's just the details that I got wrong because I wasn't considering quantum gravity. And he said, okay, you win, John Preskill. So that's that bet. One of the other people who was involved in the bet, Kip Thorne, didn't concede, as far as I understand. And so he's a bit of a holdout. He's sort of saying, well, I'm not sure these string theorists really understand all that to my satisfaction. So that's fine. That happens. And when you're talking about theoretical physics, people can disagree. So getting the entropy of the black hole and the temperature right were pretty big steps. You know, we were sort of feeling kind of pretty confident, and none of the other ponies of, you know, approaches to quantum gravity are able to calculate with precision those things. But really, if you've only understood the temperature and the entropy of that thing, there's more to understand. And in particular, how is it that when I throw something into the black hole, how is the information actually going to come back out again? Where was Hawking's original ideas? Where did he go wrong? Because it seemed like his calculations were pretty robust and there wasn't really much space for disagreeing with his methods. And that's where the last little subtopic that I'm talking about comes in a little bit. So I'll try to finish up within about the next 5 to 8 minutes or so, and hopefully that won't take us too far beyond where I'm supposed to be at this point. I'm aiming to try to finish at 5:02 because I started at approximately 5 past. So what I want to introduce is an idea called holograms. Now, I don't know how many of you have actually seen a hologram. Maybe you've seen, I don't know, the Science Center or something, but the key thing about a hologram, and it's made using lasers, and it's really cool how they make these things, but what is possible to do with holograms is to encode full three-dimensional information into a two-dimensional image. So if you're old enough to have had years ago, have a credit card, certain types of credit cards in a certain epoch, one of the security features they had was the little holograms on them. And so that's just a picture of an old credit card of mine with a hologram in it. So the key thing is that if you want to represent the higher dimensional, three-dimensional information, if you can make a hologram, you can encode that information on a two-dimensional surface, which is, you know, smaller than the 3D thing that you were trying to represent. Mm-hmm. Now, black holes have some tantalizing properties that indicate they might behave like holograms. And one of the reasons is that when we talked about that Bekenstein-Hawking of the entropy of the black hole, it turned out to scale like the area of the event horizon, like proportional to the surface area of the black hole horizon, not to the volume of the black hole. And that's quite different to the entropy with, for example, for a hot gas in a piston in a steam engine, the entropy there scales like the volume. So what this gives us a clue of is that black holes whose entropy scales like the area, maybe somehow they're behaving like a hologram. And in 1993 and 1994, Gerardo Tuft, who won the Nobel Prize in Physics some years earlier, and Lenny Susskind, who was my PhD thesis supervisor, took this idea ultra seriously and proposed that actually our four-dimensional universe involving gravity is secretly three-dimensional, just like with a hologram. And they didn't actually have a working model of this idea. So when in physics, in theoretical physics, you haven't got a very good model yet, but you've got a suspicion that this is an important idea, you elevate it to a principle. You can't prove it, so you just say, I propose that the holographic principle is true. And then let me see what would flow from that. And these ideas were tantalizing and interesting sounding. And then it was a few years later, in late 1997, when a young, bright person by the name of Juan Maldacena discovered the first working model of holography by inventing a brilliant new idea known as the Dscft Correspondence. And he got there by taking stacks of strings and D-branes and taking very insightful limits of them, and derived this brand new idea that physics and quantum gravity physics in a higher dimension could be described using a hologram theory that didn't have any gravity and lived in one less dimension of space. it's probably not an overestimate to say Dscft is one of the most important discoveries in theoretical physics in the last quarter century. Maybe I'm overstating it because I really like it. So of course, this is partly a matter of taste that I'm expressing. But I think the fact that it sparked so many conversations with people in other parts of physics, like modeling the quark-gluon plasma, the RIC, and modeling condensed matter system using ideas from Dscft, and even trying to apply it to cosmology, and then the overlaps with quantum information theory, it's been quite a fertile area for cross-talk between different subfields of theoretical physics. And Dscft originated from string theory and not from other approaches to quantum gravity, but a bit over a decade later, it was recognized to be a much broader idea. This idea of Dscft holography doesn't actually require string theory at all. So if you're not particularly fond of string theory, you can still get along and study Dscft holography, teaching you things about quantum gravity without having to take bets on which pony is going to be the right pony for the theory of quantum gravity. So for my last few minutes, I'll just say a tiny bit about Dscft and how it applies to black holes. What it is, it's a beautiful and powerful duality. What we mean by the usage of that word in this context is to say that it's an equivalence. The two theories of having quantum gravity and ADS living in a higher dimension, and the hologram conformal field theory, the CFT, living in one lower dimension, these theories naively look very different from one another. One has gravity, one doesn't. One's in a higher dimension, one's in a lower dimension. But in fact, you can see that these two theories are actually equivalent to each other. And ADS side of the correspondence refers to having full quantum gravity with all the complications of that in the case of a negative cosmological constant. In this case, the conformal field theory is the hologram for quantum gravity and ADS. And there's one new space dimension that emerges from the CFT to describe the quantum gravity physics in ADS. For those of you who worry that that's not really experimentally viable, there's also a version of the correspondence for a positive cosmological constant, like having a positive dark energy, as our universe apparently does. And this is called the Dscft correspondence. And in that description, it's the time dimension that emerges in a technical sense. Now, the cool thing about Dscft is that it applies when the ADS and the CFT are not just empty. So if you, in particular, if you would heat the conformal field theory up to a finite temperature, then what is described on the other side of the correspondence turns out to be a black hole in anti-de Sitter space with the same temperature as its Hawking temperature. So heating the CFT up to the Hawking temperature is dual. It's the hologram for the full physics of the quantum black hole in anti-de Sitter space-time. And this is really mega cool from a theoretical perspective, because it means you can recruit the power of Dscft to study quantum black hole physics in detail. And in particular, the question of if I chuck quantum information into my black hole, am I eventually going to be able to get that information back out of the black hole before the black hole, dies from radiating too much? And so focusing on the entanglement between the aspects of what's going on has been a key vector for progress. And evidence has accumulated that classical space-time geometry, the stuff that we think of as just the fabric of the space-time, the fabric of the cosmos, that's built up out of quantum entanglement in the hologram theory in a universal way, which is super interesting and was really not expected initially. And for a black hole that's emitting Hawking radiation, detailed study of how that radiation entangles with the black hole on the one hand, and or with any infalling stuff, has shed some very deep light on the ability to recover information that falls into a black hole. And that specifically the details are best worked out for a low dimensional case called ADS2, which is dual to something called the SYK model. The details are very technical and I don't plan to get into that, but I'll just say that Hawking's original semi-classical picture of saying classical black hole plus quantum matter is the right way to analyze things, there's modifications of his picture. And in fact, it does look like information is probably rescued. So with that, I'll just show a slide which has some resources for further reading if you want to know a bit more about this kind of stuff. There's a couple of really good articles written by science writer George Musser that were published in 2018 and one late last year. And also for those of you who are not in possession of physics degrees at a level that would enable you to delve into this stuff a bit more, there's a website called theoreticalminimum.com where you can go and watch some video lectures by Lenny Susskind, who's a very dynamical and understandable person to learn from in lectures. He doesn't really like to write his thoughts and ideas all down in textbooks, so they decided, well, okay, he's fantastic at giving lectures, so let's just videotape the hell out of him. So there's a ton of lectures that you can find on YouTube by Lenny Susskind, and a lot of them are really good. He can be very amusing and wave his hands and pretend to be subatomic particles or whatever. Some of my style in giving talks is a function of having learned from him. Anyway, I think I probably talked too much, so let me just be quiet and listen for questions and do my best to answer them in a way that's respectful of the people asking them. Thank you all for your attention. I hoped that at least it gave you a flavor of some of the ideas that people like me think about. And the exciting thing is that over the 30 years I've been in the field, there's some really big discoveries made, at least progress in our understanding, that leads us to think that, I don't know, maybe it won't be another 100 years before we finally understand quantum gravity properly. Who's to know? There could be some big surprises around the corner. We don't know for certain. Would you like me to try going to the Q&A and answer the questions in order, or do you have a different format that you would like to have?
The Q&A function is great.
Okay, so what I might do is to try taking them in order, and I'll try to get through all of them, regardless of how many questions there are. So the first question was about slide 6. So let me just whiz back to slide 6. And you said, how do we know that the formulae to calculate properties of black holes, such as temperature, are accurate? Is there some way that we can possibly test such properties? Do you mean test experimentally, I'm going to guess? One of the problems that is difficult to set such a thing up is that if you take an astrophysical black hole, like for example, that black hole that the Event Horizon Telescope imaged the light ring around, and you ask, what is the Hawking temperature coming from that black hole? Is it measurable? Could we do some experiments to actually check what's going on? And the answer is, for those particular black holes, they're big enough that their Hawking temperatures turn out to be quite cold, and colder than even the cosmic background radiation. And so that doesn't seem like the astrophysical black holes that were formed in gravitational collapse of burnt out stars. It doesn't seem likely that experimentally we'll have a good handle on that anytime soon. However, if there were smaller black holes that weren't created from gravitational collapse that were made, for example, in the Big Bang, called primordial black holes, those can be a lot smaller and those can turn out to be a lot hotter, and they could have a Hawking temperature that might be measurable. Other people have chosen to take a route of saying, well, even if we don't get the ability to directly be able to play with black holes and their Hawking properties and measure their entropies, then could we come up with sort of analog situations using the same principles of quantum physics and do experiments on Earth that would with analogs of black holes that would teach us some of the things that we need to know. And some people like Bill Unruh based at UBC and others have proposed analogs of those things, and people have definitely found evidences of the physical mechanisms that can produce Hawking radiation. Just the prospect of being able to study them directly with black holes where they're really be measurable, I'd say, is kind of slim, the prospects of that. I hope that does some job of answering. So at the moment, we're mostly relying on theoretical principles, but let's just say that those theoretical principles are not just wild wacko things that we bring in from nowhere. They're the same physics principles that we use to describe other phenomena, like the quantum physics of photons interacting with electrons in the standard model of particle physics and so forth. So we can't just bring in entirely new ingredients for how these things work that violate the principle, the other applications of the same ideas elsewhere in theoretical physics. So our imaginations might seem to run riot and really run wild, but we work under some pretty significant constraints that if we come up with a new idea, it has to, at the very least, not spoil some agreements between theory and experiment that have already been very well established. I'll try answering that question in the chat after I've done the Q&A ones, because I think it came last at the moment. I hope I've done a somewhat of a good job for answering the anonymous attendees question around slide 6. So I'm hopeful that there will be ways that we can test the physics principles, although we might be a bit unable to get very direct evidence. Sometimes the best you can do is look for indirect evidence of the physics you're trying to study. The next question I want to go to is the one from Mukesh Shrestha. I apologize for not being excellent at pronouncing various names. I sometimes muck up English ones, by the way. So it's yeah. So does the quantum entanglement break inside a black hole? That's a really brilliant question. So if you, for example, have a Hawking photon that escaped from the black hole and its partner fell into the black hole, there's some entanglement between the outgoing Hawking radiation and the black hole. On the other hand, if ingoing stuff, which is another ingredient, is ever going to, the information that goes in is ever going to come out in terms of the Hawking radiation, it seems like probably the infalling stuff is also going to have to entangle with the Hawking radiation. So there is something in quantum information theory referred to as the monogamy of entanglement, that if, for example, I am maximally entangled with, I'm A, for example, if suppose I'm A and I'm maximally entangled with B, then B cannot be maximally entangled with C, because you can only be maximally entangled with one other little microscopic thing in that situation. So this question of exactly how the quantum entanglement breaks between produced Hawking photons and the interior of the black hole and outgoing incoming radiation, infalling stuff and outgoing radiation, that's really the key question of where it's at in the field. So that's a very sophisticated question, and working through the details of that is what the very recent progress that I was talking about that's been made in particular in the last 2 or 3 years, where people have come up with low dimensional and simple, admittedly, models of certain kinds of black holes, where we really understand that process of how the entanglement gets broken and how that story then yields return of the information from the black hole, and involves aspects of holography, quantum gravity, and also quantum information theory has featured very prominently in this story of trying to untangle, what's happening with quantum entanglement around black holes. So I hope that does a reasonable job, at least, of answering Mukesh's question. And if it doesn't, they can always add one to the mix later on if they want to come back and re-ask something after the others have asked theirs. So let me try moving on to then Lady Shantai, is that the way you pronounce it? Question: what excites you the most about gravity? Oh, well, what a question. Let's see. Well, I've kind of described aspects of it today. I mean, at a very basic level, I like skiing, although I haven't been skiing in a few years because of injuries and stuff. So skiing would really suck without gravity. So, I mean, that's one aspect of gravity that I really like. It wouldn't be so exciting if we could ski on the moon, even if there was snow there, and even if we could put humans there, because the gravitational accelerations are so much smaller. But, what excites me the most about gravity is it's the force that seems to be the most pertinent to the dynamics of the cosmos as a whole. It's the most democratic force, in the sense that everybody feels gravity. Even gravity itself feels its own gravity. There's another force where that happens, the strong force, where the gluons feel the strong nuclear force on themselves. And in the weak nuclear force, there's a version of that. And gravity is the force, though, that's felt democratic by absolutely everybody. If you have any energy, and you certainly do if you have rest mass, or even if you just have energy without any mass, then everybody who has energy or momentum feels gravity, everybody. So I kind of like that fact that gravity is a universal democratic sort of force. It's not picky about who it chooses to talk to. And that means that it's also a long-range force. It can reach out to the very edges of the cosmos. The other long-range force that we know about is electromagnetism. But that to have a long-range electromagnetic force in the universe, you would have to have an overall charge, electric charge for the universe. And as far as we know, on average, the universe is electrically neutral. So, those are some of the things that excite me about gravity, but also that they're, intimately involved in the physics of black holes. After all, without gravity, we wouldn't have any black holes to be studying. Right, so let me get to Eduardo Reyes's question. How do you entangle photons experimentally? I have to admit that I'm a theorist, so I'm not really perhaps the world's best question to ask about this. But basically you have some sort of, microscopic setup, some aspect of atoms, you heat them up and then you let the atoms get excited and then they fall back down to their unexcited state and they emit photons. So there are ways that you can use atom and molecular physics to be able to create entangled photons. And that has to do with the process of how they're born and how those pairs of photons, for example, are produced in like the Einstein-Podolsky-Rosen thought experiment, which was pretty important in people's thinking about developing those aspects of quantum mechanics, Bell's theorem and all that stuff, is by using particular atomic and molecular processes that you understand relatively well that produce those photons in entangled ways. So it has to do with the specifics of the electric force, basically, that keep the electrons in orbit around the atoms or molecules, and maybe you use lasers or other sorts of clever experimental apparatus to be able to produce those sorts of aspects. But again, I'm a theorist, so I'm possibly not the best person in the universe to ask about this. But basically it has to do with atomic and molecular optics physics, or sometimes referred to as AMO physics, is the realm that you'd probably be looking at if you tried to Google it. So I hope that goes some way towards answering the question. Again, if it doesn't do well enough, then come back and add something to the end. So Jeffrey Chu has a question. What do you think are the most pressing engineering challenges towards acquiring experimental data to consolidate quantum gravity theories? Ooh, that's a really interesting question. Let me just say that there is a very wide range of theories of quantum gravity out there on the market. I think some of them are built on considerably shakier foundations than others. The kinds of quantum gravity models that I've been talking about, string theory and holography, are what is sometimes referred to as top-down models, in the sense that we start from very tiny microscopic ingredients that we have very good reasons to believe that we understand how to do that, and then try to reach down towards the physics that we see out there in our relatively low energy universe. There are other ways of going about it and saying, well, let's look at what I've got in the universe around me and try to work from a bottom-up perspective to say, well, what are the possible things that I might be able to measure, and then say, what kinds of theories might give rise to my ability to access these things experimentally. So I think, it depends what is the most pressing engineering challenge in relation to trying to experimentally test quantum gravity. I think the answer to that depends pretty sensitively on what kind of pony you're betting on for what describes a theory of quantum gravity. So there are some people who say, well, quantum gravity gives rise to these predictions about, how there might be dispersion and the motion, how photons move. Maybe some things can go faster than light, some things can go, different speed of propagation for light or gravitational influences, or maybe neutrinos have a different speed of propagation, et cetera, et cetera. And so I think there's a pretty broad range of things there. And again, I'm not the most qualified person to really talk about engineering aspects because I'm not an experimentalist. It's not been trying to pass off the question, being lazy. It's just that I really genuinely don't know. So, and if you asked me what an average quantum gravity experiment is going after, there would be a number of reasons why I would sit there and nitpick about, oh my God, I really don't think that model of quantum gravity you've got is realistic. There's the following deep physical, theoretical physics reasons why we believe that probably isn't a good theory of quantum gravity. So then you get into the question of arguing over, are my principles more righteous than your principles? And that is largely a matter of taste. We're hoping that what will happen over the years is people have all these possible different roads towards quantum gravity. They look like they're different pathways. The best kind of outcome intellectually would happen if we learn from each other's approaches, and maybe various aspects of some of them will end up being pointing towards what will eventually be the quantum theory of gravity that we'll agree on. There is also a more depressing possibility that we'll never have enough to be able to really tell which theory of quantum gravity is true. So I think for the moment, that conclusion can't be definitively reached, and we should just reach our imaginations in all the directions we can exert them in, because after all, theoretical imagination is a hell of a lot less expensive than building experiments. And when we're theorists, we should try to do as much imagineering as possible before we go to the experimentalists and say, build us a thing to contraption to measure this. So we have to try to, keep in mind what other people's theories are trying to do and try to propose experiments that are not extremely singular in committing to one particular theory, but that a number of different approaches to quantum gravity think that it might be a good idea to measure this thing, and then we can go ahead and try to do those experiments. So let me try to speed up a bit because I've got several questions waiting.
Professor Pete, you had a question in the chat that came up before some of these questions. So
oh, sorry, beg your pardon. Yes, my bad. It's just a little difficult to see all the different windows. So let me go to, I think it was Yechiel question was the first one.
Yeah, that's the only one in the chat.
Right. So do you believe in jumping string theory could be used with a hologram, maybe in order to have another version of another reality, or possibly send a hologram for the afterlife? Those are very interesting questions. I'm not sure what we mean by another reality. There could be maybe, our universe is, we live on a brain in a higher dimensional universe, and maybe there's another set of brains over there with some other creatures that have different rules of doing physics. And maybe perhaps there's another reality over there. They've got a holographic description of their hologram, whatever, and we've got a hologram over here. Then one of the ways that we might imagine in such a imaginative scenario, we would still be able to communicate with each other using gravitational signals. But gravity is a pretty weak force, so we'd have to do some pretty big, noticeable things in our universe to be able to send a ripple across to the other beings on this other brain to be able to, for them to get a message that we're out there. So maybe that's a possibility. I think at the moment that's still probably a little bit within the realm of science fiction rather than, theoretical physics, but it's a good idea to think about these kinds of questions. I hope that goes some way towards answering Yechiel's question. And if you would like to ask a supplementary, please try and stick a question in the Q&A, and I will do my best to try to answer that as well.
Just to cut in before we continue answering questions, just in the interest of time, we will say that there are 3 questions in the Q&A right now, and that's excellent, that's amazing, but we're going to close the Q&A, I think, from this point onward, so Professor Pete can answer the remaining questions, and then we'll wrap up for the night.
Alrighty. So there's a question, another question from Mukesh, I think. So based on slide 11, is space-time emergent from strings, or where are strings present in space-time? Great question. I mentioned quite a bit earlier in my discussion that the equations of general relativity, which are less sophisticated than the equations of string theory, even the equations of GR have this sort of self-consistency story, that space-time tells matter how to move and matter tells space-time how to curve. Now, in string theory, both matter and space-time are described by strings. And so what kind of spacetimes strings can live in and what kinds of D-brane spacetimes we can create, those have to be solutions of what you might refer to as sort of a big self-consistency conditions. So strings don't like to propagate in any old spacetime. They have some standards. They're like, okay, if you obey the following properties, then that will be a solution of string theory. But these other ones, no, sorry, can't make those ones. So string theory is a bit picky that way, and so basically the question, the way that we answer your question is to say, let's try in certain circumstances to solve those self-consistency conditions of string theory to propagate in a given spacetime. It's not that we put the spacetime there and then we stick the string into it and the spacetime can't fluctuate. Anything but. In fact, the spacetime is dynamical, and in string theory there can be regions in our theoretical description where there isn't even a classical spacetime geometry to be found. Those are called non-geometric phases of string theory. And so it isn't always the case that in string theory there even is a big fat classical spacetime that would act like a stage pertinent to our thinking from general relativity experience. Given in the interest of time, I think I'll just quit there and I'll stop sharing my slides and then just go to looking at the remaining questions. So a question from 1234, in your very rough estimate, how many years do you think physicists will solve the problem with quantum gravity? 5 years, 10 years, 20 years, 50 years? Any of the above? I really don't know. If I could predict precisely, what I would do is that I would go and borrow money and bet on the financial markets about this or something, right? If I actually knew how long it was going to take before we cracked the puzzle, fully understanding quantum gravity to everybody's satisfaction, then I could make some money intellectually, among other ways, doing that. Not that actually making money is my primary or even secondary or tertiary priority. So I think it's anybody's guess right now, and even the most famous theoretical physicists in the world, of which I'm not one, they probably aren't able to answer that question with clarity either. So maybe it's just around the corner. I'm kind of hoping that we will eventually solve the problem with what quantum gravity is just before I die. So I will have had time to work on it for my career, and then I'll retire, and then maybe when I'm like 93 years old, somebody will eventually, solve the problem of quantum gravity, and I'll get, hopefully, the intellectual satisfaction of seeing that before I kick the bucket. But then, that's a bit optimistic, I think. So that's done with that question, I think, and then I'll move to the very last one. This one is from Dan, and it asks, do gravity waves escape the event horizon, or are all the gravity waves detected generate outside of the event horizon of a merger? So this is about what happens not when you just have one black hole and you chuck a small rock into it, the kinds of thought experiments I've been talking about so far, but this is about where you have, say, two black holes, and initially they may be a certain distance apart, and then they go into what's called an in spiral. They sort of go around each other. The center of mass is fixed in the middle. And then there's, because of the big tidal forces and other strong gravity going on, eventually they will merge with one another. And it isn't until after ring down has occurred, when there can be quite a lot of wobbling of the merger thingy, and it isn't until a certain amount of time that it settles down into what's called a stationary black hole, a single black hole. So the gravitational waves that we can detect, for example, in LIGO and Virgo nowadays, with amazing quantum optics and other experimental, astonishing engineering there for building these gravitational wave detectors, what they are looking at is the ripples in the fabric of space-time were thrown off from the merger when it's still in its vibrating phase. And there's so much energy, like absolutely ginormous amounts of energy in those gravitational waves, more than the luminosity of all the stars in the universe for a few seconds. And so, yes, those gravitational waves that we measure in our detectors didn't originate from inside the event horizon of the eventual settled down black hole after all of the stuff has happened. So they're generated outside of the event horizon of the eventual stationary black hole. But it's a fascinating question to think about where what's called the apparent horizon, which is a region where there are trapped surfaces, they're called, where light is trapped inside them. And working out all those very complicated details is really interesting, and that's the domain of people who study gravitational waves. That's not my primary area of interest, but I think it's really fascinating, and gravitational waves provide some of the first very, very good strong field tests of general relativity. And some people believe that maybe they'll even, because, if you're having two singularities merging into one and the process of doing all that, maybe we can get a window using gravitational waves onto those questions of what lies beyond Einstein's theory of classical gravity. Maybe it will give us some hints about the nature of quantum gravity. People still argue about that. I think I'm done. And you've been all very patient, and I've gone 15 minutes over answering all the questions, but hopefully that's given some satisfaction to the people who were asking the questions. And it's been a real pleasure being involved in this awesome event you've organized. And I hope that, it was useful for people.
Yeah, thank you so much. Your talk was amazing, and thank you for answering all the questions. And thank you to everyone who stuck around for the questions as well. In terms of what's coming up next, tomorrow we have our second black hole lecture, and then after that we have our astrophotography workshop, where you can learn how to take some pretty awesome pictures of space using just your smartphone. So hopefully we'll see you all tomorrow. Thank you again to Professor Pete for the excellent talk, and I hope everyone has a great night.
Okay, bye for now. And thanks for the invitation. It was a real thrill to be part of your amazing event.
No worries. It was our pleasure to have you here.